lecture we left off with talking about pressures, and that 101 kilopascals is equal to 1 atmosphere is equal to 760 millimeters of mercury. And if you remember, we talked about that 760 millimeters of mercury actually having to do with how tall this mercury column is standing. And so if that mercury column stands from here to here, 700, oh, nice drawing, 760 millimeters tall, then we're at standard conditions, which we also have classified as 1 atmosphere. Now, what occurs with gases, why they cause pressure, it has to do with the movement of the molecules. What we have in the air is we have all these gas molecules that are flying around. Their collision with the surface actually causes the pressure. And so what we're seeing here, this 101 kilopascals, is actually a force per whatever area they're colliding with. And at sea level, we end up with this 101 kilopascals. We're about to do some problems of converting between each of these. So I put the conversions up top here, and it says, what is the pressure in kilopascals of 3 atmospheres? So what we can do is set this up like we've done in the past. You start out with your 3 atmospheres, and then set up, like I always say, the goalposts. And let's get rid of atmospheres because they're going to divide out. And let's put our kilopascals on top. And so what we do is put our 101 kilopascals, which comes from there, and we look at 1 atmosphere on the bottom. And so we multiply those two together, and we come up with a value for kilopascals. If you look at this, what's happening is our atmospheres divide out, and we get the appropriate answer. Same thing happens with the millimeters of mercury in kilopascals. We can start this problem out exactly the same way. We start out with our 1250 millimeters of mercury. I want to get rid of millimeters of mercury, so those guys are going to go on the bottom again so that we'll divide out. And we're going to put kilopascals on top. At this point, we look back up at our conversions. It's 101 kilopascals, so we put that in, 101 kilopascals. We put 760 millimeters on the bottom, and then it's a little bit of calculation. 1250 times 101 divided by the 760. And you guys can explore this last one. Okay, moving on. A manometer is another way to measure pressure. Where a barometer is measuring the atmospheric pressure, the manometer helps us measure a pressure in a chemical reaction. In this particular case, as we look at this manometer, we actually have a open-ended manometer. And so to describe what's going on here, at this end, what we have is we have this open end, and so it's feeling pressure from the atmosphere. So this might be 760 millimeters of mercury that's actually pushing, driving this down. Now, over on this end, we have this pressure coming in from some sort of gas chamber. We might have a chamber over here that we have a chemical reaction going on in, and what's going to happen is this is going to give off some gas. Now, the pressure that's being given off on this side is if the columns on either side, these mercury columns right here and right here, are equal, then the pressure inside the chamber, inside our gas chamber, and the pressure outside our gas chamber would be equal. But since it's pushed down a little further on this side and a little higher on this side, the pressure inside our gas chamber is actually higher than the pressure outside. So the pressure inside would be 760, or the outside pressure. And if you notice above it says P naught, the pressure inside the container, which is P up here, is equal to P naught plus the height of the mercury as it's pushed up. If the mercury was pushed up higher on the gas chamber side, it would actually, the outside pressure would be higher. And so this is what's called a closed-ended manometer, and so we're able to calculate the pressure. It's simply a U-tube where we capture a gas and then watch the mercury shift. And down here you'll notice they have the equation written out. The change in pressure is equal to the pressure minus P naught. And so we have, we're able to figure out what the pressure inside of our gas chamber is. All right. Some variables that we need to consider when we're dealing with gases. First of all, we already talked about pressure, and notice I didn't put that in the list, but we need to include that. So we have pressure, and then the other thing is what is the volume of the container that we have this amount of gas contained in? Another one is temperature change. As we increase the temperature, it has an effect on the container and the number of molecules that are actually in the container itself. And so as we move on, we're going to start looking at two of those variables at a time, and then we'll come around to looking at all of those variables simultaneously. And so we're going to start to explore that. The first one is this Boyle's law. And if you'll notice down here, what we have is two chambers, and one chamber has a smaller volume for the gas, and you'll notice the needle is pointing to a higher pressure. As we decrease the volume, what occurs is the pressure is going to drop. And so we have this relationship as the pressure, or I'm sorry, as the volume decreases, the pressure is going to increase. And so that relationship is called an inverse relationship. And so what we want to consider here is that the inverse relationship is normally written as pressure is equal to some constant over volume. But I don't like fractions, and I'm sure you guys don't either. So what I want to do is I want to get this V off the bottom. And so what we end up with is we end up with the equation P times V is equal to a constant. Now, as long as I don't change the temperature or the volume of either one of these containers, we have two situations. We actually have pressure 1. Change some color here so we have a little color in this. Pressure 1 and volume 1 is equal to the constant. And we have down here pressure 2 and volume 2 is equal to the constant. And since this constant, as long as the temperature and the number of atoms inside don't change, then this relationship of K should be the same. In other words, K should be the same in both cases. And so what we end up with, instead of just P1 V1 equals a constant, we can actually look at a container and say that P2 V2 is equal to P1 V1. So if I have an initial pressure, initial volume, and we change the volume, we should be able to predict, or we should be able to calculate what the new pressure is. And on this next screen, we'll be looking at that. So what I always do when I'm doing a problem like this is I start out and I say we have the container and the pressure is 1 atmosphere. So I'm going to start out and put P1 is equal to 1 atmosphere. The next thing it says is and the volume is 5 liters. So I write down V1 is equal to 5 liters. And is compressed to 2.5. And so there's our V2. So I'll write down V2 is 2.5 liters. And we don't know pressure 2. And so what we need to do is we need to set this up. A moment ago I said we go P1 times V1 is equal to P2, which we don't know, times V2, which is 2.5. And so we solve this. We get P2, we divide by 2.5 on both sides, and we end up with the total pressure of the system to be 2 atmospheres. Okay, I'm going to stop right now so that we don't run out of time, and we'll try to do another version of this, or part 2 to what we're working on, and I'll give you another one.